Hello friends, welcome to my channel. Let's have a look at a newly appeared problem, problem 2683, neighboring bitwise exclusive OR. In this video, we're going to explain a method based on initialization and check consistency. Here we are given an array called derived, which has length n. So this derived is derived by computing the exclusive OR of adjacent values in a binary array called original of the same length. So here, for each index I in the inbound, so if I equals the n-1, in other words, the last index, then derived I equals original I exclusive OR with the first element. Otherwise, so derived I equals the exclusive OR result of the ith element and I plus 1th element. So here I and I plus 1 means index. So given any derived, so our task is to determine whether there exists a valid binary array called original that would have formed derived. So we need to give a Boolean return. So here are three examples. In the last example, so this is actually very special. The one is we have only two elements. So actually for this problem, if we have two elements, the two elements in derived must be equal in order to have an original. The reason is that the first element is the exclusive OR result of the original at index 0 and the original at index 1. Now, similarly, the second element is also the exclusive OR result of at index 1 and at index 0. So they should be the same. That's why in example 3, the return is false. So because we have explained example 3, so the return for example 2 is obvious. So for example 1, so actually a valid original array that gives the derived is 0, 1, 0. So actually you can try examine. So if we flip the sign of flip the zeros and ones, it also works. So in other words, 1, 0, 1 is also a valid one for example 1. So we return true in this first example. So with that done, let's also look at the constraints. Actually, the constraints are additional assumptions for the problem. The first item is that the derived as a list has length n. The second one is that the length is bounded below by 1 and bounded above by 10 to the power 5. So 10 to the power 5 actually is a decent large one. And if the length of the derived is just 1, then we can actually examine that. So an element exclusive OR with itself, it's going to have a result 0. So that element must be 0. So this is the one thing to notice. So lastly, the values in derived are either 0 or 1. So in other words, the derived is also a binary array. Actually, this is obvious because the original is a binary array. So with that said, we are ready to do the analysis. I guess here the main point is to understand or digest the detail based on the rule of exclusive OR. As for writing the code, so it's actually very routine. First, the method here is initialization and check consistency. So because in general the element derived I is original I exclusive OR with original I plus 1. So we can first initialize the original 0. So here we can use 0 or we can use 1. Both are good. Finally, we'll explain why. Then after we initialize the first element in the original, then we can set the corresponding elements from the first one up to the last one. And then we can check consistency based on last element in derived to see if the original is correct or consist more precisely. So here in general, if derived I because derived I is given by original I exclusive all with original I plus 1. So if derived I equals 0, it means original I and original I plus 1 should be the same, right? So we can set original I plus 1 equals original I, right? If derived I is 1, basically it means that original I plus 1 and original I is different. So we can set original I plus 1 equals 1 minus original I. In other words, if original I is 0, we set original I plus 1 to be 1. If original I is 1, we set original I plus 1 to be 0, right? So this way we can set all the elements. So when we add the last index n-1, so basically we know derived n-1 equals original n-1 exclusive all with original I. Then depending on the value of derived n-1, we can know what original 0 should be. But we have already initialized original 0, so this is where we check consistency, right? So if derived n-1 is 0, it means original n-1 and original 0 shall be the same, right? So now we just need to check. If they're not the same, we're going to return false. If derived n-1 equal to 1, it means original n-1 and original 0 shall be different. So if they are not different, so we need to return false. So this is the logic. So after the checks, if no returns, we return true. In other words, we have a consistent original 0, right? So this means that we have an original list which derives the derived, right? So before we write this code, actually we can make some remark. So here we can set original 0 to be 0 or original 0 to be 1. Both options actually work. The difference is in the full original array, it's a flip of 0 and 1. So as we explained in example 1, so if we set derived original 0 to be 1, then the original will be 1, 0, 1. And if we set the original 0 to be 0, so this is the valid original array 0, 1, 0 in the explanation in example 1. So the deep reason, actually a deeper reason, is that flipping of 0 and 1 does not affect the resulted derived list from the original based on the rule here in the main statement. And this is actually due to the operation rule if you think a little bit carefully, because the exclusive all basically is this: the same number yield 0, different yield 1. Here same and different we mean binaries numbers. So in other words, if you have 1 and 1, so and 0, 0, we're going to get 0. And 1 exclusive with 0, or 0 exclusive with 1. It's commutative, it's 1, right? So here, let me first write a code based on the above explanation. So we are going to write with some redundancy, and then later you can do some simplification. So first, I'm going to retrieve the length of this derived. So this is also the length of the original, right? So now let's initialize an original. So I'm going to use -1 times m. Then I'm going to set the first element at index 0. So we can set it to be 1. So here I will see both 0 and 1 all work. And just choose one, just the corresponding to a flip of 0, 1. This is the 1 point. So next we just need to iterate. So for I in range m, right? Then we're going to get the current result. So let's derived I. So we want to check if the current is 0 or 1, right? Let's first check the case when I is less than n-1. So in this case, we know you can think of this current equals original I exclusive original I plus 1, right? So then the logic will be clear. If current equals 0, So it means original I and exclusive or with original I plus 1 equals 0. It means that they are the same, right? Because original I has already been set. So we are going to set original I plus 1 and to be original I, right? So this is when they are the same. So if current equals 1, it means original I and original I plus 1 are different. So we're going to set original I plus 1 equals 1 minus this one, right? So this is the case for inbound index. So excluding the last one. Otherwise, it means that I equals n minus 1. Maybe you can write it like this. If I equals n minus 1, this is more specific, right? And then we're going to check again if current equals 0 or not. Because in this case, the current, so let me write, now the current equals original n minus 1 exclusive all with original 0. So now when I equals n minus 1, we don't need to reset original 0 because we have already initialized it. We just need to check consistency. So if current equals 0, we hope original n minus 1 and original 0 to be the same, right? So if they're not the same, so we're going to return false. So if original n minus 1, which is already set, does not equal to original 0. So in this case, we are going to return false. This is the one thing. Another thing is that if current equals 1, so then we hope that they are different, right? If original n minus 1 equals original 0. So in this case, we return false again, right? So if after this for loop, especially after we finish the consistency check, so let me make a remark. This is a consistency check. So when I less than n minus 1, this is set up the original or propagating the original based on our initialization. So after the for loop, if nothing has returned, so we just need to return true. So here actually this code follows closely the analysis above. This is very verbose. So let's first make a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic case. So here let me print out the original, if it's true, right? So original. So let's see. Yeah, for this example, here we have 1, 0, 1. If we use initialization 1 here. So now if we use 0, so we're going to have 0, 1, 0. Let's check. Yeah, 1, 0, 0. So this is inconsistency with the first example valid original. So with that said, basically that's about it for this problem. So here is an extension. So for sure I can think of simplifying the code. So actually the solution to this problem can be very short. But here for explanation and for digest, so we write with some redundancy. So here I'm going to comment out this. Yeah, with that said, basically that's it for this video. Thank you.